So thank you everyone for joining us to the first and hopefully one of many Open Catalyst challenges. Hopefully you guys all got a chance to attend the challenge overview right before this. If you didn't or you missed it, that is recorded, so make sure to check it out after the discussion. And you probably all got a chance to take a look at the schedule, but we already kind of went through the challenge overview. We'll begin with our runner-ups giving their talk and followed up by some Q&A, followed by the winners and likewise Q&A, and then we'll end with a discussion whether about the challenge or about the project in general or any lingering questions you guys may have. It's exciting to see a large number of you here, so hopefully we can have a fruitful discussion. I do ask that during the presenter talks, just hold your questions to the very end. But other than that, feel free to turn on your mic, open your camera if you wish, and just interrupt us and ask anything. With that being said, I guess we can go ahead and get started. As previously mentioned, our runner-ups were Annapolis AI. Congratulations to you guys. And I guess we can go ahead and we have pre-recorded talks for you both. So we'll go ahead and play those and we can continue afterwards. I think audio.
Can you share the sound?
Oh. Yeah, I can. Abhishek, I think you have to do it on your end.
Yeah, let me see if I can figure it out. How about now?
Good afternoon, dear colleagues, and my name is Ruslan, and here I represent our team in AI from the Innopolis University. It's in a small city in Innopolis in Russia, and we would like to introduce our solution to a well-known Open Catalyst challenge and discuss some details below. And as we know that the carbon dioxide is an extremely disturbing greenhouse gas, which is released from the excessive use of fossil fuels. And the idea is to convert it back to fuel or use it as building block for production of polymers and large-scale chemicals. And this idea during the last 10 years was proven to be very promising. But the main problem is that carbon dioxide molecules are very inert and stable. It's because the carbon atoms in CO2 are the highest oxidation state +4, and therefore it's necessary to develop efficient electrocatalysts for carbon dioxide reduction processes, and different routes of electrochemical CO2 can be realized through multiple electron transfer, both in aqueous and organic solutions with suitable electrocatalysts. And the carbon dioxide can be converted into small C1 molecules like formic acid, carbon monoxide, methanol, well-known methane, and also C2 and C3 building blocks like ethylene and propylene. And the main task on the catalyst community is to develop catalysts with the lower potentials and increase selectivity to desired products. And our frequency analysis on this awesome Open Catalyst 20 data set revealed that the presence of adsorbate dominates subdistribution of absorption energies, and exactly can be exploited for regression. It was done before. But in our case, we are limited by the presence of out-of-domain, both in catalyzed and adsorbate examples in validation data sets, and we have to create a more general models instead of selected machine learning approach. And the first approach was to use niche activation functions as more regularized compared to switch. And the result is small improvement in in-domain and also in out-of-domain examples by mean absolute error both in energy within threshold values. Okay, as we know that different graph neural networks have recently achieved a great success in predicting quantum mechanical properties, both for molecules and materials, and exactly now for catalytic processes. And in previous works, so-called MPNNs with appropriate message, update, and output functions, they really outperformed several well-known descriptor-based baselines, and these eliminate the need for complicated feature engineering, but an important task is to design MPNNs that can generalize efficiently to larger graphs like catalytic processes, and generalizing to such larger graphs, and making these models more domain specific for catalysis for us seems to be pretty challenging. And at the first approach, we decided how to featureize surface adsorbate and interatomic interactions in the bulk catalysts by itself, by introduction of first column matrix, which is simple global descriptor, and it mimics the electrostatic potential. But this formula, we can see, it can also handle interactions between atom itself and between two different random atoms. And its extension, a logical extension of Coulombic matrix called Evel-Sum matrix, which was designed for periodic systems, and it also models the interaction between atoms in periodic crystal through electrostatic interactions. And also the next approach is Zine matrix, which captures features of interacting atom in a periodic system with a very low computational cost, or just extension of the Zine matrix. And here they are defined by the lattice vectors and Cartesian unit vectors. Exactly, this functional form has no physical interpretation compared to Coulombic matrix, but it captures some of its properties like periodicity of crystal lattice, which we observe for catalyze exactly, and infinite energy when two atoms they overlap. Okay, so the metal non-metal bond properties, mainly they are determined by the number of unpaired and paired electrons of d orbitals, and also SD, PD and PP interactions between both adsorbate and surface atom and bulk atoms itself in catalyzed. Our description of local structure in terms of the coordination of valence atoms, which was explained above, is a representation of atoms and surrounding environments, which is derived by converting the standard notations into one-hot vectors, just using a dictionary of the valence subshell orbitals. So here you can see that S1 and P5 and S2 elements of the orbital field matrix correspond to the coordination numbers of sodium atoms and chlorine atoms, which surround the sodium side. And the next, from this sparse matrix, we designed the representation of local chemical environment by considering the sum of all weighted vector representation of all atoms. Here O is the representation vector of atom K, and W it's weight of an atom, which measures the contribution of the atom. And the atom at site P in the chemical environment can be represented using the theme as follows. Okay. And we also present a simple and versatile representation, which is applicable to any deep learning models, not only graph-based. It involves labeling the binding site atoms of the underlexed Bayer surface geometry by binary value, like is this located in the threshold by 1 and 2 from sum of atom radii or not? And if it's located within, exactly we know it as interacted atoms by 1. And this idea was inspired by the Ulis et al. Work, but we haven't used the relaxed structures to extract coordination environment. And inspired by the well-known and popular in recent 2 years OrbNet architecture, which used featurization of molecules in terms of symmetry at the atomic orbital, we propose so-called OFM network flow from the orbital field matrix. The first step, we have low-cost featurizations, which was performed both for atoms like nodes and bonds between atoms like edges. And then these node and edge attributes are processed by the embedding layer and message passing layers to produce transformed node and edge attributes, and then transformed node attributes for the encoding layer, and each message passing layers are extracted. There are new representations, and in the end we have passing through the MLP-specific decoding networks. And in our case, it's about 4 layers. And then in the end, we have node-resolved energy contributions, which are calculated node-wise, just by summation. And the final energy is just one body summation of the nodes, like in Berner-Perinella approach. And also Jorgensen and all, they have proposed novel neural message passing, and which was very pliable for both molecules and materials by extending the SHNet model. It was extended by an edge update network. This allows the information exchange between atoms to be dependent on the sending and receiving atom, and this simple extension led to a very high improvement of SHNet by itself. And next approach, so very well working DimeNet proposed by Click-Pera. And he solved, and his colleagues, and he solved this directional embedding by noting that an atom by itself, it's rotational invariant, and this invariance can be broken by neighborhoods that interacts with this atom. And those atoms who inside of the located inside of these cutoffs. See, and each neighbor breakups the rotational invariance of the second, and in this case, they introduce additional degrees of freedom. And they also represented these rotational degrees in their models. And in the end, they get a very effective DimeNet architecture. Okay. And we also choose these architectures to be featurized by both force matrices, orbital field matrix, and binary representation of catalyzed. And here you can see the performance of our models on the evaluation data sets, and the bar charts, they show that both mean absolute error and an error within threshold values. They improved more for edge update net here and OFM net after introduction of the orbital field matrix and binary labeling of catalytically active side. And Ewald sum is also seems to be the most effective descriptor among Coulomb and Zahn matrices. And the last approach, which we provide here, is the collaboration between well-known graph representation and the supervised learners, like gradient boosting. And as gradient boosting algorithm, we choose CatBoost, which creates symmetrical trees and boosts them weighted way. And so we tuned also parameters of integrated framework. And here you can see a small improvement both in mean absolute error and energy error within threshold. But the main advantage, as we see here, and opportunity for active learning, the ability to extract uncertainty from CatBoost model. We see that it can be very useful for high throughput screening based on active learning approach. Okay, and we also see the challenge for community to create a detailed reaction mechanisms for modeling of processes and high throughput screening, which is based on the absorption energies of all intermediates together with reactants and products, and maybe in future it will be also activation energies. And this will be extremely useful for both creation of reaction charts and screening. It was noticed above. And also just small warning that this research exposed 150 kilograms of carbon dioxide during training on Tesla V100s. Okay, so we have more obligation to reduce, convert it back to something more useful than CO2. Okay, and this is our small team. Thank you very much for your attention, and we are ready for your questions.
He phrased it perfectly. We'll open the floor to questions now. Feel free to unmute yourself, go ahead, ask your question, or if you want, you could just send the question in the chat and some of us will be on the lookout for them. I can start us off while people gather their thoughts. So one interesting thing I liked about something you guys talked about was the uncertainty quantification with the CatBoost. You didn't go too much into it, but I was curious to what some of those metrics look like, or did you guys explore like how reliable those uncertainty metrics are, or kind of any further analysis on that note? I know it wasn't part of the challenge, but it was interesting to see part of the talk.
Okay, so thank you very much for such wonderful questions. Such approach of estimating uncertainty. So the way how to estimate uncertainty using gradient boosting was very nicely clarified by paper by Prohorenkova and co-authors from Yandex. So there are a lot of approaches, for example, how to estimate uncertainty, both data uncertainty and model uncertainty. And in this case, uncertainty estimated can be estimated as variance of small decision tree predictors on our whole gradient boosting model, and how it can be useful, because currently we are running a project with the Hilver Center. It's also on catalysis, but not on heterogeneous. It's about homogeneous molecules, complex molecules, and there are the same problem that we have unexplored chemical space of about 80 Ks of very large organometallic molecules, and we have to calculate catalytic mechanisms for all of them. And for these, we have to estimate uncertainty as metric for active learning. For example, in the initial state, we use clustering of our whole data. We create a baseline model, then upsample, update this model with the examples with the top uncertainty. So this is a way how to, I would say, create a more accurate model with a less amount of data. This means that we save time together with, for example, DFT calculations. And I think this will be a very nice way how to, for example, explore further this data set. For example, it will be very useful if you want to explore the whole mechanism, and there should be several intermediates, and we also can obtain the uncertainty not only on the single structure but also an ensemble of structures, which can be correspond, which can be presented during the whole catalytic mechanism. So and we have checked on that organometallic organometallic complexes data set, and it showed that it can really improve, this strategy can really reduce the number of DFT calculations about in 4 times. And there is a lot of opportunities to check it in Open Catalyst data set. And also, yeah, and also we can use it, for example, in addition to other descriptors, for example, classical descriptors by material projects, and several representation, I would say, vector representation like one-hot vectors.
Yep. Thank you. Yeah, certainly. I think even the Open Catalyst project, we've been starting to think about uncertainty just because it's important for downstream applications. But we could probably talk more about that in the discussion at the end. We have a question in the chat. I think you went over this in the presentation, or maybe provide more details. How many and what GPUs were used for your trainings? Okay, we had 3 GPUs, Tesla V100s, and usually we filled 2 of them. It's 3 V100 GPUs on the whole lab. And yeah, exactly, the difference in training and difference time here is very large. For example, it can take 3 days to, for example, to train some of the directional message passing graph neural networks, and for example, 1 day for SHNet. And exactly, we have to, for example, sometimes to plan for several weeks our experiments, for several months, and they are still running. And we know that, for example, we haven't submitted to our challenge the best model, and I think it can be published soon. Okay. Any other questions? We could probably take one more. We have plenty of time at the end, so whatever we don't get to, we can talk about at the end. Any last questions?
I think in few of your results towards the end, it felt like evolve some matrices didn't help as compared to, let's say, Coulomb matrix. Do you have an intuition for why was that the case?
Yeah, I have an intuition because our catalyst surface is periodic by itself, and the DFT calculations were set in periodic basis. In the authors of this data set use periodic boundary conditions, and L-sum matrix compared to Coulomb matrix can also handle such periodic interactions, and that's why I can interpret this intuitively. Yeah.
Okay, just out of the interest of time, just in case people planned around the other schedules, we can move on to the next group. And we have plenty of time at the end. I know we set a cutoff, but I think we have plenty of time. We could stick around and answer any other questions. Perry, you want to go for it?
I can take it forward. So next up, we'll have a presentation by the winning team of this year's Open Catalyst Challenge, Microsoft Research Asia.
Hi everyone, I'm Shu Xinzheng from Machine Learning Group, Microsoft Research Asia. Today I'm on behalf of the machine learning team participating.
Sorry, just want to make sure the sound's okay, right?
Hi everyone, I'm Shu Xinzheng from Machine Learning Group, Microsoft Research Asia. Today I'm on behalf of the machine learning team participating in the Open Catalyst Challenge on NeurIPS 2021 to present our winner's method, the Graphomer, which is a general purpose backbone for molecular modeling. Our teammates are Guolin Ke, Li He, Tianyan Liu, and three interns, Cheng Xuanying, Jia Chengyou, and Yihan He, from Dalian University of Technology, Tsinghua University, and CMU respectively. In today's talk, I'd like to first quickly go through the challenge, then introduce our method Graphomer, and finally show the experiment results. The Open Catalyst Challenge is from NeurIPS 2021 computation track. It is derived from Open Catalyst project, which is a collaborative research effort by Facebook AI Research and CMU. It aims to use AI to model and discover new catalysts to address the energy challenges posed by the climate change. If we could find a kind of catalyst which can drive the chemical reaction of conversion of renewable energy to other fuels, such as hydrogen, then it offers the potential of scaling to nation-size grids for renewable energy storage to address the global warming issue. To find low-cost catalysts to drive these reactions at high rates, huge number of dynamic simulations are required. However, the quantum mechanics simulation, for example, density functional theory, is extremely time-consuming and costly. Therefore, it would be great if we could find the cost-effective solution for chemical reaction simulation by using AI model. For this purpose, Open Catalyst Challenge provides 0.66 million molecular relaxation systems by DFT simulations to develop a good AI method to better model the catalyst. The system contains a catalyst and an adsorbate. The different 3D structure of adsorbate maps to different energy, and the structures is changing towards lower energy structure. This changing process is called relaxation. And at the end, the energy of the adsorbate is low and the structure is stable. For each system, the initial structure is provided, and the goal is to predict the final relaxed energy. There are two tracks. The first one is a direct track, which requires the model takes the initial structure and directly predicts the final energy, and no additional training data could be used. The other one is relaxed track, which predicts the relaxation trajectory step by step, and the inner trajectory data could be used for the training. Considering that direct final energy prediction is more efficient and more challenging, we participate the direct track. Typically, graph neural network are used to capture the geometric and physical knowledge in AI-based molecular simulation. However, the expressive power of graph neural network is limited. It could be proven that the expressive power of GNN is bounded by first-order WL test, which means that it cannot distinguish some important substructures. Also, deeper GNN does not equal to more expressive power. Deep GNN suffers from the oversmoothing, which means that it cannot benefit from being deeper, wider, and larger, although this is the trend of today's deep learning models, like Transformer. Therefore, in this computation, we choose to use Graphomer model, which is a general-purpose backbone for molecular modeling, and published by our team on NeurIPS 2021. Graphomer is built upon a standard transformer model and equipped with 3 simple yet effective structure encodings. The first one is spatial encoding. The first one is spatial positional encoding. It's used to model the topological relationship between atoms, such as the shortest path length between the different nodes in the molecular graph. The centrality encoding is used to measure the importance of an atom in the molecular graph. And the third one is the age encoding, which aims to model the age information in the molecular graph, such as the chemical bonds. Graphomer is designed for both the strong expressive power and also the capability of capturing structural information in graph. In the paper, we prove that the conventional graph neural networks are special cases of Graphomer with reduced expressiveness, which means that the Graphomer should be strictly more powerful than conventional graph neural network models. Actually, Graphomer is not only theoretically sound, but also achieving outstanding experimental results on many benchmark datasets for molecular simulation and graph learning. For example, it wins the first place of KDD Cup 2021 quantum chemistry track. And Graphomer is a very general model, which could be used for both 2D and 3D molecular graph modeling. The differences of 3D molecular modeling with 2D is that there is no chemical bonds, but only the position of each atoms and the distance between atoms. All the properties of a molecule depend on the distance between atoms. Therefore, considering that there is no explicit chemical bonds to connect atoms, to model the 3D moleculars with Graphomer, we choose to use fully connected graph, which can be easily processed by the self-attention layers in Graphomer. Besides, there is no more edge encoding, and we choose the Euclidean distance encoding as the spatial encoding, and the sum of the distance encoding over edges on each node as its centrality encoding. First, we leverage the Gaussian basis functions used in SpinCom to encode the distance. And second, for each node, we sum all the distance encoding over its edges as its centrality encoding. For Open Catalyst Challenge, there are 2 more additional modifications. The first one is that the boundary condition of catalyst is periodic. Therefore, we first repeat the unit cell along with the XY axis, and then cut off the atom by the distance of 9. The second specific modification is that we can use multitask learning to improve the performance of Graphomer. Except for the energy prediction, we can also predict the delta position between the initial position and the final position for each atom. Therefore, we set up an equivariant 3D cross-attention height to predict this task. After calculation of the softmax attention probability, it will be projected to the 3 directions and then calculate the weighted sum of V along with 3 axes respectively. This is the overall architecture of Graphomer for 3D molecular modeling. The spatial encoding and the centrality encoding will be derived from the distance encoding, and the relaxed energy is predicted from the virtual node token. And other item token are processed by the 3D cross-attention to predict the delta position between initial and final structures. The training details are listed here. We use 48-layer Graphomer, and the parameter is shared every 12 layers, which is inspired by AlphaFold 2. The batch size is 64, and the learning rate schedule is linear warm-up and decay. The total training step is 1 million, and it takes about 1.5 days for training on 8 NVIDIA A100 GPU cards. And the final results are assembled by 31 models with different data position and random seed. On the public leaderboard, we obtain the best performance of the direct track, and the final result will be released at the December 7th. Thanks very much for your watching. Please kindly contact me through the email for any problem.
Cool. We have a couple of members from the Microsoft Research Asia team. Would be happy to take questions. Yeah.
Thank you, very shaky. I'd like to add a few words before the QA. Okay, first, we'd like to thank and congratulate to all the organizers for Open Catalyst Challenge. Thank you for hosting this amazing competition and generating the unprecedented the large scale data set. It's really amazing, and we do enjoy the competition. And second, I would like to congratulate to the Innopolis AI team, the GymNet team, the SpinCom team, and all the participants to obtain the great achievements. We believe that the molecular dynamics is a very super important area, and with great efforts by the awesome data sets, the wonderful computation, and all the amazing participants, we could push the frontiers of this area together. And finally, I want to say sorry for that because I cannot speak too loudly because it is midnight. Typically, it is 3 a.m. in Beijing time, so I cannot speak too loudly. So very sorry. And the model we used in the computation is called Graphomer, which is based on our NeurIPS paper this year. So you are welcome to visit our poster at poster section 2, and I will copy the link in the chat box. And all the code, model scripts, and configurations to reproduce our results will be released on our Graphomer GitHub repo in maybe a couple of weeks. Won't take too long time, but because we are cleaning our code and upgrading the transformer backend to FireSec. Thanks very much to the Facebook AI research team for providing such high efficient transformer backend. But there are still be some dirty works, so please kindly stay tuned. And thank you all again, and all the organizer and the participants for the amazing competition. And I think we are ready for the QA section. Thanks very much. Okay. So any problem?
I see Ruslan raising his hand. Go for it.
Yeah, I have a question. That's a very wonderful concept on using metal-centered, atom-centered graph normals. And my very curious question was, how did you choose the central atom? Exactly, I think that it was made to make the structure, I would say, invariant, both rotations or any other translations. But yeah, the main question, how did you choose the central atom to encode the structure around them, and is there any principle around this?
Yeah, very good Very cool question. We use the gravity center for the system to be our center items to in the PPC process to cut off our system to calculate and process by our graph model.
Because I would say this idea can perfectly fit to such area as homogeneous catalysis, where we have a central atom of, for example, any transition metal and organic ligands surrounding them. And here we have also a correlation, for example, on the impact of ligands which surrounds its bond orders. And that's also our research topic, and it will be really very interesting to we also one of my colleagues who also present here, and during this summer he did about the same job. He took the central atom of our complex and then encoded other surrounding atoms by the beginning from the closest atom around them, exactly, and adding atom number embeddings and distance embeddings. Okay, that's, I think, so this can confirm us that we were on the right way. Thank you very much. That's very inspiring.
Thank you. Thank you.
Siddharth, did you have a question? I saw you raising your hand, I think.
Yeah, actually, yeah, first of all, thanks for the great presentation. And I was just curious about, so you mentioned that you used FAIR-seq for the transformer architecture. So just from the implementation point of view, did you kind of merge the OCP code base that we have separately with the FAIR-seq code? Because they are like very separate, and like, having all the, let's say, data loading capability and the model architecture from FAIR-seq is a little bit of a challenging job. So how did you solve that?
Thank you. Do you ask the how we leverage the FAIR-seq to process the graph data in the OC20?
Yeah, I'm saying that how did you eventually sort of use the FAIR-seq framework with the OCP code base, because they are both very separate, right? And you mentioned that you eventually used sort of a transformer base from FAIR-seq. So from an implementation point of view, like how was that? Because this is definitely very tricky and like not straightforward.
Yeah, actually, it's not that very complicated because we mainly use the FAIR-seq to use its transformer backend, but the data loader and the data interface we use the OC20 the preprocess code, which is incorporated by the torch geometric. So actually if we process a graph by a transformer, then each item will first be encoded by some item embedding, and actually it equals to the token embedding in the sequence processing for the transformer task. So we just replace the token embedding by the item embedding, and then the distance encoding in our talk introduced by the 3D graphomer is used by attention bells in the self-attention module. So we just calculate the correlation between items and items, and then we add the attention bells as derived from the distance encoding. Then we can use the FAIR-seq backend, transformer backend.
Cool. Yeah. Thank you so much.
Just to expand on that real quick, did you guys incorporate Graphomer into the OCP code base, or you guys just used our data loaders or data sets and had your own?
We just use your data loader and data process script. Thanks very much for providing the script. It's very, very, very helpful.
One question that I had was, I noticed that in your result slide, the performance on the out of distribution adsorbate and both splits was noticeably worse than the other two subsplits. Did you have intuitions on why that might be the case?
Very good question. We also observe this phenomenon, but we don't know how to explain it. I prepare some question for the organizer, and one of this is this is one of my question. Why the OOD performance is different with other test subset?
I guess just to follow up on that, how you mentioned that you used an ensemble of 31 models on like different partitions of the data. Was there anything specific about how you partitioned the data? Or uniformly random?
Yeah, we random partition is just like 31 fold partition for different. Oh no. We have 29 fold data partition, a random data partition, and 2 fold for all the data set training. All the data sample used for training. So we have 21 models for our final in-sample submission.
Got it. Thank you. We have a question in the chat, and then I see Roman raising his hand. The question from the chat is, how does your model compare to DimeNet++ in terms of time and memory needed for inference?
DimeNet++ is a awesome baseline because we take a long time to beat it by a very marginal gain. And DimeNet is really quick, but I think in contrast, the upgrade version, the GMNet is another great baseline because we also try our model on the relaxation track, but it's not perform very well because the GMNet is a very strong baseline, and we are very curious about how to be. Also, the SpinCom is another very good baseline, and we are very curious about how to beat them by the transformer model. I don't know, maybe the two track are facing different problems and some models they have their advantage to handle different problems. For example, we see the demand also participates the direct track with their noise node paper, but we also try their technology on the relaxation model and also be beaten by the GMNet and the SpinCom. So it's very interesting.
But for the direct track specifically, did you have any intuition on like how the runtime of your model compares to DimeNet++?
I don't have a specific time. Maybe you guys have trained the DimeNet++ and the GMNet. I just remember that our model is trained about 1.5 days on 8 GPUs. Do you have any idea how about the training cost about the DimeNet++?
That sounds right in the same ballpark. DimeNet's trained, I think, with similar compute. Correct me if I'm wrong, someone here, but that sounds normal.
Okay, thank you.
Cool. Roman, do you want to go next?
Yes, thank you very much. And thank you very much for this interesting talk. Could you please give more details on taking into account periodic boundary conditions? Because if you just increase amount of cells, even in this two-dimensional periodic boundary condition, quasi-two-dimensional periodic boundary condition case, you need to take into account that each atom you have in this extra cell is needed to be recalculated somehow, or you have a problem with connectivity again on the border of this increased cell. How did you manage all these tricky moments with the model? Thank you in advance.
Yeah. Thank you very much. I think it's very good question. Actually, in the official OCP repo, there are two kinds of method to process the PPC periodical condition boundary condition. One is called for dynamic and one is called for static. And actually, we use the static in the direct track, and then we replicate duplicate the unit cell. And actually, we also try to use the dynamic and it treats all the homo items to as the one items and connect the other items by multiple edges, and it is the default setting in the GMNet and DMNet plus, I think. And I think the transformer model is not very good at to produce such dynamic PPC process, because the multiple edges between the two atoms will introduce multiple distance encoding, which means will introduce to multiple the attention bias in our transformer model or self-attention modules. But we observe that multiple attention bias in the self-attention module will badly affect the performance because it cannot capture the really or the exact the attention bias, which means the distance between the items. But it is much better for graph neural network based method to process the PPC condition.
So you could overcome this problem with offsets. I see.
Yes.
Thank you.
Thank you for your question.
We can maybe take one or two more questions. How? Go for it. Do you want to ask your question?
Hi. So first of all, congratulations on winning the first place in this competition. So my question is more relaxed. So you have mentioned you have tried a lot of models, and I wonder. So first of all, how long did your team spend on working on this competition? And second is how did your team collaborate with each other?
Very good question. We participate in the competition about 1 to 2 months. We start. I remember we start our work from the August, and the final submission is at I think October 6 or 5 or 6 in Beijing or American time. And we have 3 team members, and we 7 team members, and the last one is our manager. so we briefly have some discussion with him, and other team members were all involved in our computation, and we discuss brainstorming and try I actually run some experience, propose some new modifications, more new gains for the model's architecture. So we collaborate with each other by very closely discussion, brainstorming, and some experience results, some experience conduction with that in that way. Maybe I hope I can answer your question.
Yeah. Thank you.
Any last question for Shushin before we move on to the discussion phase? I will take that for now. So congratulations once again, and thank you for joining at this late hour all the way from China. Next, I'll hand it over to Larry to lead the discussion session.
Thanks, Abhishek. Thank you everyone for joining, and kudos to our winner teams. It's very late in both Russia and China. So thank you for you guys. So we'll start off the discussion by really just opening the floor to anyone. So please feel free to unmute yourself, or you can raise your hand and Abhishek, Mohammed, and I will monitor. Or if you prefer to post a question in the chat, feel free to do that. Before we start off though, let's just warm up everyone a little bit by asking the participants and anyone, did you guys have any feedback for us and anything you would like to see in the future challenge? I saw someone in the chat. If I butcher your name, I apologize. Is Alexi Corwin?
Yeah, thank you very much for this nice nice challenge. I would like to ask whether we'll continue this this challenge as a benchmark. Will rest as a benchmark, or it will transform into something else? So will leaderboard will be open, and can we update the results and send you models and so get in place? Thank you.
Larry or Abhishek, would one of you like to provide a little bit more answer other than yes?
I think the test leaderboard is going to be up, at least for the foreseeable future. We don't have any plans of taking that down. So the evaluation server and the test leaderboard will be up. The test challenge data set and a leaderboard on that, we would like to make it up, put it up, but we haven't really discussed and thought through exactly what the timeline on that looks like, or what all we will release from that. And with respect to future challenges, it is very likely that we'll hold a challenge in the future. Again, the specifics of the task, the data set, all of that might evolve from this year. But yeah, hope that provides some context. Larry, was there anything you wanted to add there?
Yeah, I think it's important. We'll keep the original leaderboard that's up there right now. We'll keep that up there as long as possible, and likely for many years to come. The reason for that is within the academic literature, it's super important for people to be able to compare the results and to have those consistent baselines through time is really important. For the challenges, it's kind of interesting to see if people are overfitting to that leaderboard. And that's why one of the reasons why challenges are really interesting, because it's a whole new data set. People do it, it's one snapshot in time. So we'll probably refresh the challenge data set each year, and probably the challenges will be different each year. But that leaderboard and what you see up there, that's currently public and everything right now, that'll stay.
All right, thank you, Larry. Thank you, Abhishek. And we have another question from Shu-Xing Jin. If you want to unmute yourself.
Hi, hello. So I prepare some questions. The first one is, how could we really demonstrate the usage of the machine learning models in the material science? For example, the battery discovery.
Larry or Zach, did one of you want to?
Sorry, one more time, Shujin.
Okay. How could we really demonstrate the usage of the machine learning model in the material science? For example, the battery discovery. Do you have any idea?
Yeah, I think there's kind of two parts to this question. One is we obviously applied this to a very specific application, for the catalyst, specifically for renewable energy storage, and there's a lot of other applications out there that we could apply this to. So I think, and there's a lot of really important ones, both within the climate change community and other applications as well. So it is one thing that we're keeping in mind, and we are looking into, can we create other data sets which are specially purposed for other applications. So that's something that we will and continue to look at. We are focusing on climate change related applications, and that's our primary focus. So we probably won't go too much farther from that, but batteries, carbon capture, etc., might be, or just other renewable energy storage applications such as hydrogen generation could be something that we look into in the future. The other part of that is what was I going to say? So what was the I'm blanking on the other thing.
Anything to do with experiments or?
Let me think about it. Anybody else have a?
Okay. Thank you very much.
Yeah. Hey, this is Zach. I think I would also add to what Larry said. There's one direction where we can continue to see how well we can make the models match computational chemistry, and there's still a lot of room to go in that regard. From my perspective, as someone who comes at this from the computational catalysis point of view, I'm super excited about how good the models have gotten over the past year, and it really wasn't clear how much progress we were going to see. But probably another factor of 2 or 3 in the metrics would get us really excited. And so there's still quite a ways to go just in terms of making our understanding of the catalysts themselves better. So that's one direction. And then the other one, as Larry was saying, we can also think about how to explicitly see how useful these models in experimental discovery. And that's something that is quite common in the computational chemistry, computational catalysis community. Right, there's a lot of research groups around the world who do nothing but try and model these things and say how they can use those insights. But both of those are really interesting questions moving forward. I don't think any one of those is the only thing to do right now. But the models have already gotten quite exciting in both regards.
Which reminds me of the second thing I was going to say, which is linking these results up to experimental results. I think is super important for the field. So we can keep measuring force MAE and energy MAEs and all that sort of things for absorption energies. But at the end of the day, what matters is, can we predict experimental results? So I think hopefully what we'll see in the future is more experimental results, and see if we can actually explore the entire pipeline and not just a computational side. Okay. And hopefully that'll be something we can look into next year as well in the competition.
I would also encourage all of you, I mean, research centers, all of you have access to academic collaborators, right? Pretty much every engineering chemistry department has people doing materials discovery, computational chemistry, that sort of thing. Creative uses of these models for other fields is I think going to be also very exciting. And so I'm really interested to see what else we think of besides just the core catalyst things that we've been thinking about. There's a lot of opportunities, like batteries and other things, right? So many different things we could apply these sorts of ideas to.
Ruslan, do you want to ask the next question?
Yeah, I would like to continue the question which I have asked in the end of my short presentation. So I think that the one thing that can broaden the catalyst community and increase the value of this data set is to create opportunity to, for example, to build a free energy diagrams for several mechanisms. And I think this is the problem which is the most important for any catalyst researcher. For example, no matter does he works on carbon dioxide, electrochemical reduction, or conversion of methane. And I think it will be very nice, for example, to work on creation of easy to use API, which can build a free energy diagram and solve the optimizational problem. For example, the most energetically preferable route, for example, from initial product to the end. And I think this is just also another topic for another, I would say, challenge, for example, or another benchmark. For example, not to predict just diagrams, just to solve DFT's problem, and also to solve the problem which will be useful for computational catalyst community. Yeah, I think maybe you have planned to this way to create API and build free energy diagrams based on the these multi-million points.
All right, thank you. Yeah, we're definitely have been thinking about the idea of like running experiments and extrapolate the absorption energies. It's on our to-do list, and we're making progress. Hopefully, once we have some results, we will share it with the community on those.
From my perspective, I think that's the obvious, one of the obvious directions to go. And I love that you included that at the end of your slides, right? That's exactly what we were thinking about at the start of this, right? And it's going to be super fun when we can move in that direction. But 2 years ago, we didn't have any models that could work for an arbitrary material. And so I don't think we could even ask the question that you were saying for a general catalyst and a general mechanism until we started to see the results from this challenge and the open leaderboard. And so I think that's why now it's so exciting to be doing this sort of work.
Nice. And also, I'll just also ask several questions from you, dear Professor Wilsey. And I read about a lot of your papers about I would say, in-domain models for catalysts. For example, I also was inspired by your ideas to create pseudo-atoms based on the, for example, several cutoffs which interacts with the adsorbate. And I would ask question, what do you think, what should be more versatile in future, to use general narrow graph architectures, like, for example, graph normals, which were proposed, or to create in-domain models, for example, different graph neural networks, which can better represent the catalyst structure. For example, there are several interactions between, for example, adsorbate and the surface and other catalyst specific, for example, properties. For example, Jens Norskov was saying a lot of such called D-band theory. And also in several years, we have seen a DOSNet where they use density of states to predict properties of materials. So what do you think? Should it go in domain-specific, into domain-specific models, or into general models which can work both on molecules, for example, crystals, catalysts, and maybe human pose estimation? It was presented by our dear Microsoft colleagues.
Yeah, I don't know. I don't think there's going to be one approach that is the correct one, right? There's a lot of possibilities. A lot of, I would say a lot of the benefit in these more physics-inspired models like DOSNet or D-band center type models is that it's a little bit more interpretable. And so there's always going to be a little bit of pushback from the chemistry and the physics community if you have one general graph model that is completely black box and has learned parameters and you don't get insight out. So I think that's a challenge for everyone. How do you generate intuition, or how do you know that you can extrapolate, or know that you've actually learned something? We're not the only people to say that's a problem, but that's whenever you have black box machine learning, that's going to be an issue. And in terms of how much domain expertise to include, I would say most of the models on the leaderboard right now have taken sort of a chemistry agnostic sort of point of view. Maybe they have some features, but it's been very much just try and learn things from the graph. And I think there's a lot of additional data out there, right? DFT is very feature rich. There's a ton of information that's generated. And so I would love to see more physics inspired models, or things that take into account more features that are learned along the way. It's just really hard to know what the right way to do that is. And so that's a challenge.
Okay, thank you.
Yeah, one thing I would add to that is I think it depends upon the application. Where we've seen in-domain knowledge being useful is when the data sets are smaller and you don't have as much training data. What we've seen with the OC20 data set in particular is that we add in other in-domain knowledge, such, the orbital information, that sort of thing, and none of it really helps. And our intuition has been that once you have enough data, the neural networks kind of learn it automatically. But that doesn't mean that nothing will help. It's just the things that we've tried so far don't seem to help beyond, just having more data.
And also, I have just additional question, maybe to correspond to DFT specialists and also authors of this data set. So in the last 3 years, all the message passing graph neural networks in the end claiming that they were going to reach, or they reached, for example, as ARPANET, the DFT accuracy. And for example, just a month ago, I have been watching an NVIDIA presentation, and the CEO said that ARPANET, for example, just predicted the Schrödinger equation. But this question about metrics, for example, what is the value, for example, of mean absolute error or energy within threshold, or the value of this threshold which we have to reach to say that our machine learning really as accurate as DFT, and based on the Open Catalyst data set. So what is the metric, what the cutoff? Below then we can say that, yeah, we reached the quantum chemistry.
Zach, do you want to take a hit?
Yeah, the ones that we put in for energy and forces within threshold are specifically based on the heuristics that we would normally use for doing local relaxations. But you can imagine other properties where those might not be sufficient. If you're interested in electronic properties, then there's other metrics that you would use besides just what are the energies and forces. So I don't think the thresholds that we have are magical, but they are very indicative of sort of the starting point of building one of those free energy diagrams that you were sort of talking about in your own presentation. And I think bringing up what's happened in the small molecule community is super interesting, because those models have gotten so good, and they have good prior information in terms of tight binding models, and they have large enough data sets that they knew they could sort of hit it. And so I think those are all open questions, and I would love to see, basically the same question for these sorts of models is how much data, or who's the first person that can build a model to within, I don't know, 0.05 or 0.1 EV, which is about where our threshold is set. That's sort of the same question, and we obviously aren't there yet. But that's going to be super exciting as we get closer, right?
Yeah, one thing that I want to call out is that we have basically two different types of metrics on the OC20 data set. One is like the force MEEs, the energy MEEs. Those are more meant for the research community to kind of see how they're gradually improving, because you can kind of see advancements there. Where the other metrics like the forces below threshold, energy forces within threshold, etc., were more meant to be indicative of, are we getting close enough to be useful practically? And that's why we had the threshold set at thresholds which are pretty stringent. And that's why a lot of the results right now, on the leaderboard are at 1%, 4%. And I think that was meant to give us an indication like, hey, we're still a ways away from being practically useful in that case. And then one other thing that we've been kind of diving into too is how well do like the force MEE and energy MEE metrics track with the relaxation, computing the relaxed energies and relaxed structures, because they're not always perfectly correlated. We could see like a boost in the force MEE, but we might not see a corresponding boost when we actually perform the relaxations. Like it might not perform a lot better when doing relaxations. So I think it's important to kind of look at all these different metrics and also thinking about how you're going to use use these models in figuring out like how you want to optimize them.
All right, we have another guest raised, Shuxing again, I believe, if you still have the question.
Hi, okay, so sorry, so do we still have time?
Yep.
Okay, a very quick question. I noticed that many excellent works which perform well on the relaxation track, such as the GymNet and SpinCon, is based on the equivariant network. In my understanding, the equivariance is a powerful weapon for the data efficiency. But for the OC20 dataset, the amount of the data is extremely large, more than 130 million data samples. So why the equivalence still be important, and what's the future directions of this area? Thank you very much.
The analogy I use is even if you have, billions of images, I still want to train an image classifier using a CNN. I don't want to do it with a fully connected network, right? It just allows the network to better generalize and be able to find correlations that it wouldn't otherwise. And I think that's kind of what we're trying to do with the equivariant networks is what is the equivalent thing to a CNN in images to, these molecular structures and GNNs. And I think that's the way that we've been kind of discussing the problem amongst ourselves in that way.
Yeah, that makes sense.
One thing to add here is that we've tried non-equivariant models in the past. Like if you we had a ForceNet paper that we did earlier this year or like end of last year, where we used data augmentation to train that, and that gets nowhere close to the kinds of accuracies we see with GemNet, for example. So it's not a very direct comparison, like lots of things in the architecture changed, but it is some signal that equivariance seems to be helping even at the scale of data that we have.
Thank you very much.
We have Alexei with another question.
Yes, this question was a bit touched previously, but I still want to ask question and a bit comment about DFT calculations. Actually, in that data set, it was used with plane waves calculation with plane wave technique and be functional. And it's well known that this functional is not quite good for organic molecules calculation, and as well it's not good for not covalent like van der Waals interaction, so on. So this data set already includes some errors from DFT calculations. Is it possible to account for this calculation in future data set, or probably to include some another data, or probably include some calculation which that will be done with more precise quantum calculation techniques? Thank you.
I think short answer is yes, that's an obvious direction. In direct analogy with everything that happens in the small molecule space and lots of other computational chemistry things. So those are things that we're trying. But we chose the settings we did, which are not perfect, because it was a pretty good trade-off in cost versus accuracy for the sort of things we had. And we didn't know at the start of this if, for example, OC20 is, I don't know, order 600,000 calculations. We didn't really know if 600,000 was big or small, or like wildly undersized or like wildly oversized. And so we wanted to go for something where we'd have a little bit more data and then think about it afterwards. But obviously there are errors, and those are things that we need to think about. But that was just sort of some insights into how we chose those settings. Especially for the smaller side molecules, that's a very reasonable approach. But on the larger side, the errors get a little more noticeable. And we've also had a lot of conversations among ourselves. A lot of those errors are systematic, and so they should be things that the graph or other ML methods should be able to predict. But then there's going to be there is some numerical noise as well. And so there's a lot of really interesting questions about how to think about the data and use known and unknown errors in fitting these models. Does that make sense?
Right. Does anyone else have any questions?
I have a general question for the participants. We did have two tracks, the IS2RE and the relaxation-based approach. As we mentioned, no one kind of entered the relaxation-based approach. And we just curious to you guys' thoughts. What were the obvious block? I mean, I think the obvious blocker is probably compute, but were there other things that we missed or we should be aware of that like we do know that those are the best performing approaches. So the more we can encourage people going down that path, the better. If people have thoughts.
So maybe I can give some few points. A very good question because the first reason for why we don't participate the first track is that the computation cost is really large. For example, we maybe we need to take about half month to train one model, one transformer model on the entire S2EF dataset. That's the reason one, and the another reason is that I don't we don't know why, but we think the problem are totally different between the two tracks. Although they seems very similar, because just like I mentioned that we try to train some model on the S2EF subset, but the performance drops very badly. And the GymNet is a very strong baseline, so we are still working on evaluation study to what's the magic trick, how it works, and how to improve our architecture on the first track. That's the reason of from our team.
And just, oh, go ahead, Larry.
I'm just going to add something on the fact that you're saying they're different problems, and there is some truth to that. When you're doing the S2EF task and you're looking at forces, the forces are super sensitive to the distances between the atoms, and your networks have to be designed so that way they can like really get the subtle differences in the atom distances and the angular information. Whereas I think the IS to RE task is, you know, it cares a little bit about the distances, but it's much more rough because you're starting with the initial structures and you're looking more at like the global structure. And I think it's one of the reasons why the Graphformer works really well is it got those longer range interactions, which was able to kind of model the entire structure of the graph much better than like some of the models that we've looked at. So I think from that perspective, yeah, you can think of the problems as kind of being a bit different. Like one emphasizing longer range interactions and one emphasizing super precise short range interactions.
Yeah. I totally agree with your points because we actually we have some guess because we think the S2EF may more mainly focus on the simulate or approximate the DFT calculation, but the IS2RE may we can treat it like a classification problem. For example, we give a initial structure, then we classify it for the total system to the final relaxed energy. And another important point is that we agree with that the angular distance, the angular information is very important in the S2EF the S2EF problems, and we do not have such information in our Graphformer model. So we are trying to add incorporating some information in the model and try again on the S2EF problems.
Did you incorporate the absorbate information into your models at all? Do you explicitly call out which atoms were part of the absorbate, or did you train separate models for different absorbates in your?
We have a uniform model to the whole system, but we only have
so
the distance.
You didn't call out. You didn't do anything unique with the absorbate atoms.
Yeah, and we only have the distance information between each items.
Interesting.
Thanks for your suggestion.
Yeah, I just wanted to add to that point, and that's something pretty consistent we've seen where we iterate on IS2RE, and if we find meaningful results or improvements, when we go to STF, they don't really hold. So that's not just you; it is a difference in problems.
And we do think that the S2EF might generalize a little bit better because it's modeling those local interactions. And it might be one of the reasons why we're seeing the outer domain values much better with the S2EF approaches versus the IS2RE, which have a harder time generalizing.
Yeah. The actual polation problems is very important for this task.
Ruslan, did you just raise your hand?
Yeah. So, and just another question, for example, which was mentioned in summer in our discussion board on Open Catalyst, and I would repeat it again. So I was at we all know that so the main, for example, I would say Basser's molecule, it's a carbon dioxide molecule. Still absent in our Open Catalyst data set. And exactly, there are large problems because it has a lot of binding sites, both on carbon, both on the oxygen, both on the oxygen and carbon. But can the authors of this data set and DFT community still overcome this problem and to include carbon dioxide, include points with carbon dioxide? So can we solve this problem?
From my perspective, I think the problem is that CO2 is quite a stable molecule. And so if you guess CO2 carbon down, a lot of times it will just desorb. And so we could run those calculations, but a lot of them might not be very interesting. And that's why a lot of the mechanisms just start with maybe the first intermediate after you've added a hydrogen. There are some systems that really like oxygen, and you can get the CO2 to bind oxygens down, and that's a very interesting configuration. But the surface has to be quite reactive, and usually more reactive than we're looking for the CO2 reduction systems. And so most of the things that we would be interested in for the experimental side, we would just see the CO2 fly off. So there's nothing stopping us from doing the calculations. I just in most of the mechanisms, that's not the starting point because it is quite stable on its own. Does that make sense?
Yeah, thank you. And just another questions. We know that a lot of electrocatalytic processes, so usually electrochemists carry out them in basic or acidic medium. And for example, the presence of, for example, H plus and the derivatives, acid derivatives, or bases, strong bases can also reduce the potential and changing mechanisms. So what about this? Can we handle also the medium in future?
I think short answer is going along with Alexi's questions of other things that we can include to make stuff more accurate. Short answer is yes, that's an obvious direction to go, and I would love to see someone do it. If someone can come up with a potential or a force field that works for all the things in OC20 plus water or protons around, that would be incredible, and it would make so many of my friends' lives much easier. It's a little hard to imagine doing that if you can't already do it without the water around, which is why we started at this point. But it's an obvious thing that needs to happen to make this experimentally more relevant. There's still correlations that mean that the stuff in OC20 is still already experimentally relevant, but it would be really nice if we could do that additional step.
All right. Thank you everyone for the questions. In the interest of time, we'll probably take one more and then wrap up. Does anyone else have any last minute questions they'd like to ask or clarify? Alexei?
Yes. Actually, the main so to calculate energy of adsorption, we need both energy of surface with small molecule and energy of surface itself. So actually, energy of surfaces do not include it into data set. Is it possible to include it somehow, or how it is intended to calculate energy? Because in the particle, it is noticed that it can be just subtracted, but energy is not original surfaces are not included. So what is how to deal with this?
Yeah, I think that's a great point. And we actually did release. It's probably not obvious, but we did release the surface data that we used for OC20. They're not structured in the same LMDB formats that we used for training. So maybe it was probably missed in that big table. But we do have the raw trajectories for the surface data. That's where we got those references from. So I could probably point you afterwards or probably clarify that on the page, but we do have those publicly released.
All right. With that, thank you everyone for joining us in the breakout sessions. Abhishek or Mohammed, do either of you want to give like a quick closing remark before we end the session?
Yeah. Thank you everyone for joining. Thanks to all the participants for submitting entries to the challenge. Thanks to the NeurIPS competition chairs who've been doing a lot of the heavy lifting behind the scenes, coordinating all of this. And yeah, thanks to all of my co-organizers, especially Patty and Mohammed, as well as the rest of the Open Catalyst project team for helping run this challenge. This has been a lot of fun, and we'll probably do more of this in the future. That's it. Thank you, everyone.